NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Hey, good evening, ladies and gentlemen. How's everyone tonight? Good to hear, thanks. So thanks so much for coming out tonight. As you can see, our format's gonna be a little bit different. So to kick things off, I'm just gonna introduce our MC this evening. So to MC our panel tonight, we have Dr. Michael Gunson, whose day job is as the project scientist for the Orbiting Carbon Observatory, measuring the distribution of CO2 in the atmosphere. But he is also helping his colleagues bring their expertise to address emerging problems. Ladies and gentlemen, please help me welcome Dr. Mike Gunson.
Thank you, Mark. Good evening, everybody. I think that when I first arrived in California, I've spent most of my adult life in California, so I think of myself as a Californian by now. But the first few words of Spanish I learned on coming to California were El Niño and La Niña, quickly followed by cerveza, but that's a different story. These are really, really important words to everybody in Southern California because we associate them with wild, wet winters. To help us understand what happened in this past Godzilla El Niño winter, I've got four of my colleagues who are going to stand up and tell us something about their research interests and what they've understood. And before I introduce them, I was thinking on the way over here, one of the things that I grew up with in Britain was the stories that go, an Englishman, an Irishman, a Scotsman, and a Welshman walk into a pub. And then it goes downhill from there. So here I've got my four colleagues, a geologist, two hydrologists, an atmospheric scientist, and we're going to go uphill from here. So without further ado, I'd like to invite my colleague Duane Waliser to come up. After each of them have finished, we'll get back together on stage and we'll take questions from the audience and from online. Thank you very much.
Thank you, Mike. So as you know, the occurrence of El Niño always necessitates a lot of discussion, especially when it's in California. And that discussion happens in the news and it happens around the water cooler. And a lot of times it's around, is it going to be a big El Niño? What's going to happen to California in the drought? Is there going to be floods associated with the heavy rains? And those discussions that we hear about often muddle the difference between El Niño on one hand and predicting El Niño, and the effects of El Niño on the other hand and predicting the effects of El Niño. And the one objective I really have for the few minutes that my colleagues given me to talk to you is to clarify that difference. What's an El Niño and how good do we predict it versus the effects of El Niño and how good we predict those, okay? So as far as El Niño goes, this last El Niño that we had this last year was a very big El Niño. And in fact, out of the last, say, 20 El Niños over the last 100 years, it's easily in the top 3. And depending on how you count it or who's counting it, it may be the biggest. So it was a very, very big El Niño. And the two slides and pictures I have there are observations from two different types of satellites. The one on the left is taken from a satellite that uses infrared technology to sense the temperature of the surface of the Earth. And the colors on that map show temperature departures from normal of the surface of the ocean. And the reds are on the order of 5 to 8 degrees Fahrenheit over that fairly large expanse of the Eastern Pacific. And the one on the right are departures from normal of sea level, the sea level rise, sea level height. And the reds in that diagram are on the order of 1.5 to 2 feet. And those are canonical pictures of El Niño. And to demonstrate a little bit about how that happens, I'll animate, and I know you're after a computer animation, but I'm going to give you a different kind of animation. Pretend that my arms are sea level. Pretend that my arms are sea level across the Pacific Ocean, just sort of like that, where this hand is South America and this hand is Asia and Australia. Okay? So in the tropics, the winds are typically easterly. They blow from that direction over to this direction. And those easterly winds we call trade winds, right? And as those winds constantly blow across the Pacific, they push water up on this side. And there's just this tilt. The sea level is higher over in the western Pacific than it is in the eastern Pacific, and sea level is lower here. And that's sort of the neutral or normal state of the Pacific Ocean. So every once in a while, there are conditions that conspire, and the winds relax. And when the winds relax, the ocean slope lessens like that. And the combination of those reduced winds that cool the ocean surface, just like wind across your skin cools the ocean surface, when the winds relax, it cools the ocean surface. And when the sea level rises a little bit, the surface waters stay farther away from the cool waters below. And both conspire to make the water warm. So that higher sea level and the warmer waters is sort of the canonical part of El Nino. Okay. So, and that's what's depicted there. And that's how El Nino comes about. So you might ask then, well, it sounds like they know something about it. Can they predict it well? How well can they predict it? And that's where I get into this distinction between now we're just talking about El Nino and what's going on in the tropical Pacific. Because El Nino is really a phenomena confined to the tropical Pacific. So how well do we predict it? This is the official forecast from NOAA, the National Oceanographic and Atmospheric Administration, back in July. And the x-axis started back here in October 2014 and goes to April 2015. And when the forecast was initiated, it was July, last summer in July. Okay? And the vertical axis is the temperature departure in this region right here. Okay? The sea surface temperature departure. So this is positive and a warming, and these are negative temperatures or a cooling. And so in July, we had a little bit of warming. But looking forward, you know, that's in the future, what's going to happen? So they use models to predict what's going to happen, and there's a 9-month forecast rolling out here. And if you just look at the solid dashed line, which is kind of a consensus or average forecast, you can see it predicted the temperature to go up by 1.5 degrees Celsius, which is about 3 or 4 degrees more warming in the next 4 months, and continue to warm and then eventually cool. And you can ask the question, well, how well did they do to that forecast? So in July, they issued that forecast for 9 months, and now, having lived through all that and having the satellite data and the buoy information, we can actually verify the forecast. So the red dots are actually the observations. And you can see that the forecast, which started here, actually ended up verifying quite well out into the future 4 to 8 months ahead. So the message is, can we forecast El Nino? Yes, that phenomena that exists in the tropical Pacific, we know something about it and we can predict it fairly well. So then you might ask, why do we want to predict El Nino out in the tropical Pacific? There's not really that many people that live out there, right? So why do we need to predict it? Well, we found out that over watching many El Nino events, that El Nino has a pretty profound impact on the weather and climate patterns all over the globe. And one area they have a pretty profound impact is in North America. And this is a schematic that depicts the typical changes that occur in our sort of climate and weather in North America in the wintertime in association with that El Nino type pattern in the tropical Pacific. And under El Nino conditions, you'll typically find that the southern tier of the US is extra wet, the northern US and part of Canada is extra warm, and the sort of the Midwest East Coast is extra dry. And that all comes about because those changes that occur way down here in the tropical Pacific influence the circulation of the air down in the tropics, and it turns out that that in turn ends up influencing the circulation up here in mid-latitudes. Namely, that the jet stream, which just like I said, there are easterly winds in the tropics. The mid-latitudes where we live typically has westerlies, and that's where all the weather comes from. As you watch the weather forecast, it comes in on the jet stream. Okay? And during El Nino, rather than that jet stream bringing storms into the Pacific Northwest and keeping that normally very wet, it dips southward and brings the storms more towards the south. And those are the typical conditions. So I just showed you that we could predict El Nino very well, relatively well. How well can we predict these patterns in precipitation in North America or, for example, California? And so this plot should set some expectations on what we should think can happen. And what this is the October to March, or essentially the total annual precipitation for any given year in this region of Southern California, the total average. And this line represents the average precipitation on any given year, 15 inches in this area. And each dot is represented here. Each year is represented as a dot, going back to 1933. So there's one dot for every year since 1933, and it's the average precipitation. And along the bottom is an indication of what's going on in the tropical Pacific in terms of the warming or the cooling. And this is representing a cool Pacific Ocean, so it's just sort of the opposite pattern that I showed you. This is sort of neutral or in between, and this is that warming that I showed you the pattern of. And if you step back a little bit and you say, oh, wow, during these cool conditions in the tropical Pacific, which we refer to as La Niña, the average is below normal, and so we typically have drier winters during La Niña conditions. If you look at the neutral or sort of neither condition, and you average all those green dots together, even though there's a lot of scatter, you kind of get something about here normal precipitation. And if you look at the red dots, if you average them first, the average would be up here, and so you kind of have this sort of relation. But the message in this plot is really in the scatter of those red dots. You can get almost anything. The driest winter occurred during an El Nino, and the wettest winter occurred during El Nino. And there's a lot of high precipitation years during El Nino. And that's why we can kind of come to learn or anticipate, oh, El Nino may bring us a wet winter. So how well do we do at predicting that? And you can see that's kind of a challenge, right? So this is the official forecast that was issued again by NOAA back in October 2015. And it was for the following December, January, and February. So it was in October 2015, and it represents what the precipitation likelihood would be in the subsequent December, January, and February this last winter. And the greenish regions represent areas that are more likely to be wet, and the tan regions are regions that are likely to be drier than normal. And the language here is really important, and the people at NOAA and the forecasters pay a lot of attention to this language because they understand the shortcomings of what it is, and it's a probabilistic type forecast. So for California, namely looking at, say, these two regions, Northern California and Southern California, if you read the details of that scale, the forecast says for California, Northern California, you have a 33 to 40% chance of being wetter than normal. And for Southern California, the forecast was a 50 to 60% chance of being wetter than normal. But you can see it's probabilistic. It says what may be most likely, but it certainly leaves room for uncertainty. So how did it actually turn out? This is, again, after living through it all and adding up all the precipitation and all the gauges, this is a representation of the wintertime precipitation in what we refer to as the climate divisions of California. And each number here represents the percent of average over the historical average. And you can see that in Northern California, we had close to normal rainfall, which is good given the 3 or 4 years that we've lived through before that, which are all below normal. We got normal precipitation in Northern California. And down here in Southern California, you know, it was a relatively dry winter. We only received about half the precipitation that we might normally expect. So you can ask yourself, well, did the forecast, how good was the forecast? It didn't fail. It's just that the conditions that were thought to be most likely didn't occur. Okay? But it doesn't mean it failed. That was the case. So why was that? We're still wrestling with why. We'd like to think that the forecast would always be right, or the most likely condition that's being told would be the one that was manifest, but it didn't turn out that way. What was different about last year that might have taught us something, or that might teach us something? This is a comparison of those two pictures. This is the picture I showed before, and this is the picture I showed before for 2015. This is a comparison of what was another large El Nino event, 1997 and 98, and again, sea surface temperature and sea level height. And you can see, at least in the tropics, the patterns are fairly similar. So there isn't an obvious distinction between those two winters, even though the 97 El Nino event actually was both predicted well here, and it was relatively well predicted the precipitation up here in California and the West Coast. The difference might be that these temperatures off the West Coast were different than they were in 1997. You might have heard the media refer to the blob. And the blob was this extra warming occurring off the west coast of the US. So this aspect is still a research problem. The forecasters and scientists are undertaking research to try and understand what they can learn from that and maybe better anticipate and come up with the correct, most likely forecast next time. So that's what I mainly wanted to tell you. And in summary, I just want to distinguish between the phenomena El Nino, which occurs in the tropics. We know a fair bit about it, and we can predict it relatively well. Then there's the effects of El Nino, which is a much more challenging problem, and it is a much more challenging prediction problem, as you can see. And so we're working on that, and part of JPL's role in that process is to provide new and continued satellite information that will both inform that research and help advance the predictions. So with that, I invite my colleague Tom Painter to come up and talk about of the precipitation I talked about, how that manifests itself in terms of a mountain snowpack.
Thank you. Can you hear me? In the back? Okay, great. Thanks, Duane. So this is a shot from the Central Sierra in mid-February and of this year. And it looked nothing like the previous 3 years in the Sierra Nevada. So it was a beautiful sight. And we were really excited with our program to actually be able to finally measure deep snow as opposed to the stuff we've had. So Duane alluded to this, but the thing I want to start out with is if you took all the mountains of the western US and you just cut them all down, there wouldn't be much precipitation in the western US, right? And there wouldn't be the civilization that we have out here. It's the mountains that cause the lifting of the clouds coming off, the water coming off of the ocean, and that causes the precipitation here, all right? And you can see the distribution of elevation. So the Rocky Mountains in here, the Wasatch in Utah, and up into the northern Rockies, and these ranges across here. And how much of that is rain and how much is snow? Well, the vast majority of that is snowfall. All right, because we have very high mountains out here in the western US. So we really need to understand the mountain snowpack because that is our #1 resource in the western US. All right, so 2015 was a grim year, and Frank Gerke, I'm not sure if you can see it above the chairs, but Frank Gerke is the chief of the California Cooperative Snow Survey Program. All right, they gather all the information from all of the cooperators, Pacific Gas and Electric, Southern California Edison, City of San Francisco, on and on and on, to combine that information and make the snowpack information available to the state. He's otherwise known, you'll see him on April 1st talking about the snowpack, right? So he's otherwise known as California's snow groundhog. And here he is out with his bodyguards at the Phillips Snow Course up by South Lake Tahoe last year, pointing to what the previous worst year was, what the average was, what 1983 was, and then here he is on this date with no snow. This is this year on about the same date, and it was a much better feeling. There was snow, and he didn't have to put tape on his federal sampler, and of course he didn't have the governor and the head of DWR with him. But at any rate, it definitely was a much better year. How much better was it? Well, so we started out here in the early part of the year, creeping up and bumping up against average conditions, which is what this faint blue, this cyan is. And as we headed into late January, we were starting to crest above average, and in the central and northern mountains, we actually were sneaking up above average, and we were getting really excited because El Nino, the big kick from El Nino doesn't tend to come until February, March, April, when the snowpack just can really start to accumulate like crazy. And then it came February 1st and it shut off. And that was a real bummer. February was extraordinarily dry. And then we went into March and we started getting a little bit more. And then it fizzled out again. And so it's pretty grim that in this year that was about 85% of normal in the mountain snowpack, that was something to shout about, all right? But we'll take what we can get in terms of the snowpack. Oh, actually, I want to point out also, Duane mentioned that there had been previously 2 El Niños that were of the magnitude of the El Nino that we were experiencing. All right, so 1982-83, which is depicted here, its snowpack, and then the 1997-98 El Nino. Now, in terms, so I'm showing you part of that story, and Duane alluded to this, but 82, 83, 97, 98 had huge snowpacks. So, right, we got another El Nino of that magnitude, it's gonna be a huge snowpack. And just do your statistics, you know that two samples is not really that reliable, and sure enough, it didn't turn out quite like we had hoped, and we're desperately wanting. All right, so how have we known the snowpack? So we pretty much measure the snowpack the same way we have for the last century. And so this is the Tuolumne River Basin up in the northern half of Yosemite National Park. And the Hetch Hetchy Reservoir is right here. You'll see it in a second, but this is the water supply for the city of San Francisco. And these red dots, which are expanded by 3,600 times, represent snow pillows or snow courses. And I'll show you in a second what those are. But there are 8 of these in the whole of the Tuolumne River Basin, which is about 460 square miles. Huge area, right? But there are only those measurements, and then there's a big gap in here. All right, so what are these measurements? So there's Frank at an earlier time with his federal sampler, where you plunge the tube in, pull it out, weigh it. That tells you how much water there is in the snowpack right there, and you do it at 10 sites along what's called a snow course. That's been done since about 1910, and that is the main measurement of snowpack that we have. And then in the 1980s, we brought in, this was hot on the heels of waterbeds in the 1970s. How many of you remember waterbeds? See, look at that. It's amazing how few people know waterbeds. How many of you know Pong? Yeah, see, more people know Pong than waterbeds. All right, but somebody finally figured out what to do with a waterbed, and that's to put it in the ground and measure snowpack on top of it. All right, and so in the 1980s, that's when we started inserting those, but there are far more of these samples out here. But these give you a daily measurement. The problem is that they can get ice on them. Bears like to rip them apart. Bears like to sleep on them. And they also pool water on top of them. And so that makes you think that there's snow when there isn't snow. And so these remain a bit of a problem. All right, so we have not that great of instrumentation. So at any rate, those are the measurements we have, and we've done remarkably well with how poor an instrumentation we have. But this is the way that we really want to see it. We want to see it with 39 million times more coverage. We want to have wall-to-wall mapping. We don't want to have just distinct points. We want to have the whole thing so we can add up all of the water in the snowpack. So that led to the development of the NASA Airborne Snow Observatory, which we fly out of JPL and we developed here. And there are a whole bunch of words up here, but here's the plane at the Mammoth Airport. There's Mount Morrison. We get at snow depth, which we then take to snow water equivalent, which is just how much water there would be if you melted the snowpack down instantaneously. And we get to snow depth using a dual laser system, so just like in the movie Wall-E when Eva comes down, right? And so this maps topography, and we map it when there's snow on the ground, and we map it when there's no snow on the ground, and the difference between those two tells you how deep the snow is, wall to wall. The resolution is about like this, and we have all of those pixels. So it's kind of like having a snow course or a snow pillow everywhere across the landscape without an environmental impact statement. All right, so that sits on the front of the payload integration mount here in the plane, looking straight out the bottom of the plane, and then right behind it we have, for the measurement of snow albedo, which is the reflectivity of snow, or what tells you how much sunlight's gonna be absorbed by snow. We use an imaging spectrometer, and that measures the reflected sunlight in nearly 100 different colors or wavelengths. And that, the absorption of sunlight represents about 90 to 95% of the energy that goes to melting snow, right? Now, we do the wall-to-wall mapping of snow, water equivalent, and albedo. We do roughly weekly flights through the winter and spring, all the way out through snowmelt. You'll see that in a second. And we do 24-hour turnaround of the products so that water managers can have this information right away. And then we hold on to that information for the science community. And so this has really been a transitional tool for them. So getting to the core of this, the snow water equivalent, it is depth times the density. That's how much water there is in that snowpack. And we get the depth again from the plane, and then we get density from a model that's nudged by those snow courses and the snow pillows, which we do not want to see go away. We absolutely need to have those. All right, so this is the last 4 years. This was our first acquisition in 2013, and through 15, it had been the most amount of snow that we'd measured. Our program manager at NASA headquarters claimed that we started the drought, but we weren't taking credit for that. And so it was a pretty good snowpack, considering, and then 2014 came along. That was a bit grim. And 2014 was trying to hang in there with 1976-77 as the worst year on record. Then 2015 came along and just destroyed that. This is the roughly April 1. And this is an important time of the year because that is when allocation decisions are made for agriculture. The amount of water that's going to be distributed to the stakeholders is decided on in a very hard statement on around April 1st. All right, so knowing how much snowpack there is absolutely critical during this time. And in this year, so many of the snow pillows and the snow courses were melted out that they were like, we don't know. Then 2016 came along, and wow, we had nearly double the amount of snowpack that we had in 2013. We had to change all of our figures because our scales didn't go high enough. So that was exciting. All right, now I'll go to the movie. And this is going to take you all the way 2013, every acquisition that we've done in the Tuolumne River Basin. And down here, you'll see the total amount of water in the mountain snowpack. And not one of these acquisitions before this program started had ever been possible. So it's the first information of its kind. And you'll see these years kind of compressed down in here, largely because of 2016. But you see the snowpack melting away. These are the higher elevations. And Mount Lyell and the McClure Glacier are down here. And here's the grim 2015. Here comes 2016. Wham! All right, now watch what's happening here. We had a fair bit of snowfall, and then it starts to die off. But we're headed toward having a snowpack. In fact, can I back it up without screwing it up? Okay, I'll leave my hands off of it. At any rate, so as of June 1st of this year, we had more snow than we had at any point during the previous 3 years. And peak snow water equivalent usually comes about April 1st. It comes in the winter to early March. But getting into summer, almost at the beginning of summer, we had more snow than we did in the previous 3 years. Now understand, the snowpack was roughly 85% of normal. So just because that we were nearly double and we had the same amount as at peak doesn't necessarily mean that we're out of the woods with respect to the snowpack. It's simply we got some breathing room out of this snowpack. So at any rate, I'll stop there, and I'm going to hand it off to our senior water scientist, Jay Famiglietti, who's going to give you the good news that you've seen on 60 Minutes about the groundwater.
Thank you, Thomas. Thanks, everybody. So while this is changing over, I'm responsible for changing it over. So in contrast to what you heard from Tom and Duane and what you'll hear after me from Tom Farr, you saw some high-resolution imagery. What I'm going to show you comes from a satellite mission called GRACE, which stands for Gravity Recovery and Climate Experiment. And it's a different kind of mission. And the results or the information that we get is a little bit lower resolution in both space and time, meaning we can look at these data on regions that are 200,000 square kilometers or greater, which is about the scale of the size of half of California, and monthly and longer. Okay, so it's in sharp contrast to the Tom sandwich that I'm sandwiched between Tom and Tom, and so I'm going to slather on some low resolution GRACE data. This is an image that we put together in 2014, and I think it gives a sense of the declining amount of water that's stored across the whole state. So yes, we have our ups and downs, as you'll see. We have wet seasons and dry seasons. But one of the things that the GRACE mission has exposed is that we've been steadily losing water in California for some time. And a lot of that has to do with our over-reliance on groundwater and the fact that we grow a tremendous amount of food. So we're not judging about whether it's right or wrong. We're just sort of figuring out the accounting. Personally, I love to eat. I had a wonderful peanut butter and jelly sandwich before I came because it's an early presentation tonight. But I was thinking about it. So this is the magical mat? Yes. Okay, wonderful. So I was thinking about the food that I ate and how much of it came from California. Well, peanut butter and jelly. So the jelly was strawberry jelly. Good chance those strawberries were grown in California. Peanut butter, not so sure about where the peanuts came from. The bread had a lot of walnuts in it. Most of the walnuts that we eat in the United States, and most of the pistachios and most of the almonds come from the Central Valley. It takes a tremendous amount of water to do that. So we've been stressing out our resources, and it's so much stress that we're seeing it show up in these satellite images. So the mission is called GRACE, Gravity Recovery and Climate Experiment. It was launched in 2002. And I like to say that it functions like a scale in the sky that can weigh the monthly increases or decreases in total water storage, which I'll explain in a second, for large regions, which I explained already, 200,000 square kilometers and greater. If you look at those two satellites, I think I have another image here. You can see that they're not very big. They're about the size of half the height of a minivan. And in contrast to some of the other satellite missions that you've heard about from us before, where we're sensing some kind of radiation from the surface, or we're monitoring some kind of color, or we're shooting laser beams down at the Earth and looking at the travel time, the GRACE mission is really sensing changes in Earth's gravitational field. And the changes that happen on these monthly timescales are very much driven by the movement of water over the Earth's surface. And so in a simple way, what happens, if these are the two satellites, by the way, they orbit, we call it a near polar orbit. They follow each other around. They're up at 400 kilometers, and they're separated by about 200 kilometers. They orbit around the Earth. They chase each other around. Sometimes we call them Tom and Jerry, like the old cartoon, if you remember. What were we talking about? Water beds, Pong. Tom and Jerry might go back a little bit further. Yeah, that's right. Yeah, thanks. So Tom and Jerry are chasing each other around, but as they orbit over a place like the Sierras, like Tom was showing you, right? If there's snow on the ground, there's a lot of water mass. That region has gained water mass, right? It's gained water weight. And so as the satellites fly over that region, because it's gained water mass, exerts just a little bit greater gravitational tug on the satellites because there's more mass there. And so it pulls the first one down a little bit. As it's orbiting over, it gets pulled down. The second one comes in, it gets pulled down. Likewise, if these two satellites are flying over the Central Valley, which is losing water, it's losing water weight. It exerts slightly less of a gravitational tug on the satellites. And so as they orbit over the valley, they're not pulled down as much. They might even float just a little bit higher in their orbit, and the distance between them might change a little bit. So by keeping track of the vertical and horizontal position of the satellites, we're able to map out the regions around the world that are gaining or losing water mass on a monthly basis. And so like I think Tom said, those are first of their kind, for the ASO, first of their kind. This is kind of a common theme, right? We have very novel measurements that we make here at JPL and NASA. And so likewise, the GRACE data are first of their kind. The caveats are, it's relatively low resolution. Now, what GRACE is really showing us is what we call a change in the total water storage. So all of the snow, all of the surface water, all of the moisture in our soils, which we call soil moisture, and all of our groundwater together. Okay, so we call that the total water storage. And what GRACE is actually showing us is the change in the total water storage all the water shown in the sort of schematic river basin. So the snow, the surface water in the lakes and rivers, the soil moisture, the groundwater on a monthly basis. Okay? And the information that we've gotten from the GRACE mission has been more or less revolutionary when it comes to hydrology. Again, because if you've imagine never having gotten on a scale before, yet you're trying to monitor your health, and you're just kind of guessing at your weight over the years, and finally, you step on this thing called a scale. The news might not be good, but at least you can keep track of what's going on. We like to look, we gave these presentations earlier today to a visitor. I said, my colleagues always show animation, so I have to show one too. And so we're looking at the ups and downs of water storage in California. And the blues are wetter, and the reds are wetter than normal, and the reds are drier than normal. So we just went through the beginning of the California drought. This is sort of like a moving drought map, right? An animated drought map. So we can look at animations, but we don't really like to sit around and look at movies. Well, I do, but my colleagues actually do work. But we can also look at this chart. This is like the chart of the water weight, the ups and downs of the water weight for the Sacramento, the San Joaquin, the Tulare Lake basins. And here's the Central Valley shown in blue. And so we started in 2002. This finishes in November of 2016, actually March of 2016. Now this finished in November 2015. March of 2016 is right about here. I've seen the new data, but I don't have it in this plot. But anyway, we see wet season, dry season, wet season, dry season, right, of total water storage in the Sacramento. This is most of the water in California. So, we've never had this kind of information before, and it's telling us some pretty important things. For example, we can see the dry seasons, right? These troughs in this chart of our weight change, water weight change. We can see that the dry seasons are continually getting drier. We can see our drought, right? This is the current drought. Started, nominally in 2011. And so we can quantify this. So we can read the numbers off the scale. We've been losing about 15 cubic kilometers or 12 million acre feet of water per year, going back to 2011. That's more water. For reference, in California, the total amount of water we use for domestic and municipal supply is 10 million acre feet. So we're losing more water each year than all 39 million Californians use. About 2/3 of that, by the way, is coming from groundwater pumping, and I'll show you that in the next slide. But there's some embedded timescales here that are worth talking about. And the second one is, when I look at this chart, I think it's easy to imagine that maybe this drought started in 2006, and this was just a little mini El Nino, which it was. Okay, and really you can see that we've been losing water this whole time. And so this is sort of, this orange line here, when you think about that first image I showed you of the green, yellow, red, right? That was the green, and then the yellow one was here, and the red one was down here. So we've got this progressive loss of water. And the reason is that our winter rains, the El Niños and the La Niñas and the normal winters come and go. We get most of our water, most of our precipitation happens in the winter. We have good years, we have bad years. But our groundwater, as I'll show you in a second, just goes. It just disappears. So when you add them together, this is what you see. And so what I have been calling this, and what I think GRACE has revealed, is that we have chronic water scarcity, right? And a lot of this is driven by agriculture and the need to produce food. And it's not just in California, right? It's really happening in all of the main aquifers, the groundwater storage units of the world, actually. It's happening in over half of 20 of the 37 world's largest aquifers are being depleted at a pretty rapid clip. This is my last slide, and it, I think, underscores what's happening with groundwater. And so this is a combination plot of data from the U.S. Geological Survey, taken from wells in their groundwater model, and our estimates of groundwater losses from the GRACE mission. So we're looking at the cumulative groundwater depletion in the Central Valley, going back to 1962. And actually, this plot, if we were to extend it, we would see this decreasing trend actually goes back to the 30s. So this has been going on for almost 100 years. The colors in the background represent whether we have a wet period with respect to precipitation, right, greater than average rainfall, a dry period, drought periods like we're having right now, or in between, variably wet to variably dry in those light gray to light blue colors. And so, the overall message is, of course, the downward trend, right? And that's what we're trying to stop. We're trying to arrest this trend with the Sustainable Groundwater Management Plan. It's not clear that that's possible if we continue to grow so much food. So this is a national problem that we have to be thinking about. But the other message here is that during these wet periods, sure, we get a little bit of recovery. But then during the drought periods, we really hit the groundwater really hard. And then we get a little recovery, and then we hit the groundwater really hard. So that's why we have this overall downward, downward trajectory. So there are lots of implications for that. And one is that the water table is dropping quite a bit. The average water table depth in the Central Valley, so the top of the groundwater zone is at 2,500 feet. And so many, many wells are running dry. Many people can't afford to dig new wells, which cost to go down 2,500 feet, costs about $250,000. You may have to wait a year to 2 years because there's so much demand for drilling new wells. Not everybody can afford that. And there's other consequences. Streams are running dry. Look around Southern California. You don't really see a lot of naturally flowing streams, and that's because the water table is so low. And one of the kind of scary things that happens that my colleague Tom Farr is going to tell us about next is that the ground is actually sinking in some places, and in some places many inches to feet per year. So to continue with this theme of novel observations, please welcome Tom Farr.
Thank you. Thanks, Jay. A really great background and introduction to what I'm going to talk about. We can call it ground subsidence, or as I like to say, it's that sinking feeling. This is an actual picture here taken in 1977 showing where the ground level was in 1925 in an area of the Central Valley where there was a lot of groundwater pumping. So I'll explain it a little bit more in a minute. But as Jay mentioned, the Central Valley is really important for a lot of reasons. That a lot of food is grown in that area. But at the same time, especially in the southern part of the Central Valley, here in the San Joaquin Valley, most of that food is grown using groundwater. There's not that much surface water. A fair amount is brought down from the northern part of the state in the California Aqueduct and other water projects. But again, most of the water being used to irrigate those crops is groundwater. And you can see it's a huge amount even compared to the entire United States. And we're looking at the Central Valley for a variety of reasons, partly because we have a lot of data, there's a lot of interest there, but also there's a lot of places, what we call alluvial basins around the world that Jay mentioned, that are also experiencing these kinds of problems, where you have gravel, sand, and other kinds of aquifers that respond to this groundwater withdrawal in a variety of ways. And so we can use these remote sensing techniques that I'll talk about to study that. And also, of course, policymakers, the Department of Water Resources here in the state is really interested in what's going on with the groundwater in the state, and can we help them not only monitor the groundwater, but also the effects of the groundwater withdrawal and the subsidence, the sinking that I'll show you in a minute. This is one of the tools that they use, the state of California here, the Central Valley, and what they're doing is they're monitoring the water level in wells throughout the state, at least the wells that they have access to. Of course, a lot of people don't like the government asking them what they do with their groundwater, and that's a problem that I'll mention at the end. But you can see these warmer colors down here in the southern part of the Central Valley all indicate a decrease of over 50 feet in the level of water in the wells in that area over this period of time, which is the last few years. So they're really seeing a decrease in water. You probably heard that farmers are drilling more wells, deeper wells, and so we're experiencing this real strong decrease in the level of water here, not so much in the northern part of the state because there's more surface water and more precipitation. Well, going back to this image and a few others here, the problem, one of the problems that we're seeing not only in the decrease in the water, but the fact that the ground surface sinks when you withdraw the water. This period here from 1925 to 1977, the famous image with Joe Poland, who is one of the early researchers of this problem, occurred mainly before the California aqueduct was put in place and surface water deliveries came down and replaced a lot of that groundwater pumping, so that some of the subsidence isn't occurring quite as fast, but you'll see that it still is occurring. Other examples here, there's a pipeline here that they've had to shore up to keep the water flowing downhill. That's another problem with the aqueduct, of course. The aqueduct in certain areas that I'll show you has to be shored up so that the water continue to flow. Here's another wellhead here where it's clearly separated from the ground by a couple of feet. And this is kind of an interesting, it's an old gas well pipe that the farmer painted orange a couple of years before the picture was taken so he wouldn't run into it with his tractor. And sure enough, after a couple of years, it's sticking out another 1.5 feet because of the subsidence in that area. So it's clearly a problem for infrastructure and a problem for the water resource itself. Now, the technique we're using is something that I always have trouble trying to explain. It's not as easy as LiDAR or the GRACE satellites. We use a technique called interferometric synthetic aperture radar, which is such a mouthful that we always just call it INSAR for short. And what we're doing is we're collecting radar images over and over and over again, either by satellite or aircraft, over an area, every couple of weeks, every month, every couple of months. And every time we collect a second image, we can pairwise, we can basically subtract one image from the other. And radars are special because we can subtract the phases of the radar images. And what that allows us to do is look at changes at the wavelength scale of the surface. And these wavelengths we're talking about are like an inch to a foot type wavelengths. So we can see changes in the ground surface at the sub-inch level. We can see the ground changing at fractions of an inch. So what I'm going to show you here is an example of a time series that we collected over and over again over this time period of 1996 to 2002. We've got a lot more data, but this was one of my best examples, so I like to show it to policymakers when we try to explain what we can do. And the LA Basin here, and you'll see the color scale here goes from -5 centimeters, about -2 inches, to +5 centimeters or 2 inches. And what you'll see is how the ground is going up and down in the Los Angeles Basin, mainly because of pumping of groundwater. And then in the winter times, it recharges and the ground level comes back up. So if you're careful, you can watch the summers and the winters go by. As a geologist, I always have to point out the Newport-Inglewood Fault runs right through here, and that serves as a barrier to the groundwater, so you see that the groundwater changes differently on either side of that surface. So this is mainly recovering every winter. It's not a big problem in terms of subsidence or problems with the water table. And in fact, it's kind of interesting to notice that groundwater accounts for up to 50% of our water use in the LA Basin. You always hear about the aqueducts, but we use quite a bit of local groundwater. Up here is one spot, though, you might notice that didn't really recover during that time period. It just went down, it didn't come back up again. That's an area over in the Chino Basin, and they're actually aware of that. It's a problem, the subsidence is a problem, and they actually have a special board that's monitoring that. And they've actually, since this time period, 2002, they've been able to control that, and it's subsiding much less now, but they've actually had to put controls into place to deal with that. Now I'll show you another animation here that's of the area of the southern Central Valley, the San Joaquin Valley. And you'll see here the towns, Bakersfield, Fresno for reference. And you'll see the time scale here is about 2007 to 2011. You see my color bar, though, only goes one way. And that's a problem. And that illustrates what the big problem is here in the San Joaquin Valley. You see this hole developing and it just keeps going. It never comes back. Even in the winter when we get rainfall, it's just caused by the pumping in that area, and also the fact that in this area the geology is especially conducive to this subsidence phenomenon when they pump the water out. So this is the kind of thing that the water resource managers are really interested in getting a handle on, and getting a more quantitative view of what's going on. So what we've developed is a number of different products, including the animations, but things like this, where we're making color maps, and this is that feature that I just showed you, but this is a later time period. This is May 2015 to March of this year, and in fact we're adding more dates up into the current time using a satellite that the Europeans launched called Sentinel-1. And what we're able to do then is make these color maps of the total amount of subsidence over this time period, and able to show then how it relates to surface features. You'll notice another feature up here near the town of El Nido. That's another feature that's known. It actually developed about a decade or so ago because the farmers in this area have replaced a lot of their traditional annual crops with tree crops like almonds and pistachios. Those need water all year round. You can't stop growing those. You can't let your field go fallow for a particular season. So they've started developing subsidence in this area. Some other features you see here is in pink, the California aqueduct running down to give us our water. You see a canal here called the East Side Bypass, which is a flood control feature. You see that running right through this subsidence feature. There's a lot of concern that that's no longer going to prove to be a flood control feature because of the low spot in the middle. Another interesting feature is this blue line here is the proposed high-speed rail line. And I've actually been fielding a lot of questions and emails from the high-speed rail engineers because of the feature that we see. But you'll see that the subsidence actually impinges on the aqueduct as well, and I'll show you an image of that in a minute. But in this area of the maximum subsidence here near Corcoran, which you see in this time period is about up to 20 inches over less than a year, I've plotted a time history of what that area looks like. And this is another thing we can do with this essentially four-dimensional data set. And what we're showing here is a period from actually May 2014, which we've used, which I can plot because in this red line here is a Canadian satellite that we've also processed and used to create the subsidence maps. Then the Sentinel data is this continued data. And that clearly shows that the subsidence is up to about 2 feet per year in that area, the maximum subsidence in this area. So we can show in a quantitative sense what's going on. Now, I just wanted to show one more thing here. In this yellow band here is the path of an aircraft sensor that we've been using. And my colleague Kathleen Jones here at JPL has been flying this aircraft radar over and over again along the same path and able to create the same kind of data for that path. And so you see here the path of the aircraft, the California Aqueduct pathway, and then she's color-coded here in red the subsidence areas. And what's nice about this system is it's much higher resolution than the satellite systems, so we can home in on an area here that we saw in the satellite data but couldn't really kind of pinpoint what was going on. And so she's enlarged it here, and this little bullseye here is sitting right next to the aqueduct. And sure enough, you look in the center of that bullseye and there's a big well there, and it's pumping very hard, and they experienced most of their subsidence in the summer of 2014 before we gave this data to the Department of Water Resources, and they have contacted the well operators because it costs millions of dollars to shore up the aqueduct to keep the water flowing. So this is a pretty important aspect of the infrastructure of California. So I just wanted to return to this and sum up by saying that, as I mentioned, we're working closely with the Department of Water Resources. They're actually funding our work to make these maps. And you probably heard maybe in the last year or so, California finally passed regulations on groundwater in the state. And so they're using our data then to inform their decisions on how to regulate and control the groundwater use and pumping in the Central Valley. We're also expanding to other parts of California and other parts of the West and the world to start looking at other problem areas that have these same kinds of subsidence issues. So that's all I had, and I guess we can switch over.
Thanks, Tom. Stay there.
Back to you, Mike.
So with that, the fun starts. I'd like to invite my colleagues to come and sit in the comfy chairs. Oh, no Monty Python fans? Oh, thank you. Stick around, I've got more. So please, come and join us on stage, guys. And we're going to take questions from the audience and from online. If you have a question in the audience, please use the microphone at the center of the room. And we'll give a few moments for them to get comfortable.
Am I the Irish one?
Just checking, maybe. So, any questions before I kick it off? Oh, yes, we do have one. Please come up and use the microphone.
Hi, I had 2 questions about the NASA GRACE material that was shown in the presentation there. The first one is that you're using the satellite to sort of measure the gravity changes in order to detect, I guess, the subsidence, or at least the amounts of water that are there. And I wonder if I'm sure you probably have thought. So, are there other confounding factors, other issues that would be changing the gravity of how much it's pulling, and how do you account for that?
Sure.
And then I have a second question.
Right.
So, should we let Jay answer that one first, and we'll get to your second question?
Should we vote on it?
No, I voted.
Okay.
It's an autocracy
So that's a great question, and people ask all the time about things like oil extraction and erosion, trees growing, leafing out and losing the leaves in the fall, and the wildebeest migration. And far and away, the number one thing that is changing, that's affecting the gravity field, is the movement of water. So those things contribute, but they're second and third order effects. One thing that can be a big effect, and we have to correct for, is really huge earthquakes, like the Sumatra earthquake in 2004.
And also from that same presentation, you were saying that you were showing that the drought could be charted going back further and further periods, and you were saying it seems to start or decrease since the 1930s. I don't know, have you been able to disentangle how much of that is an issue of human-caused climate change, how much of that is an issue of increased human usage of water, and how much is natural variation or something?
So the reference to going back to 1930 was the groundwater depletion in the Central Valley. And so the pattern that we see there is pretty much the pattern that I showed you, and that is, we're using the water to grow food, and we use less of it in wet periods because there's more surface water available. There may be a climate change component to it over the long term as we get less replenishment of the aquifers, but we haven't tried to tease that out.
I'm kind of interested to see whether Duane has any comments about disentangling human-induced climate change factors.
I have a name for his animation. I'd like to call it the scarecrow.
That's good.
Let's not pick on poor Duane, but that's okay. It was a good animation. So what do you think about disentangling human-induced climate change?
It's certainly a subject of research right now, but I don't think that's been teased out to where the uncertainty is smaller than the part that we know. So.
I have 2 questions. First of all, is there any one feature that stands out that prevents the spread of groundwater, whereby the groundwater cannot be instilled properly? And secondly of all, this is kind of off the subject, in regard to Jason 3, was there a momentum wheel put on Jason 3 whereby the TOPAX Poseidon mission had to be ended and the satellite turned off due to the fact that the wheel failed? And so I just wondered if there was a replacement part.
I'm going to take the second one just to say I don't think any of us here are experts in Jason 3 or TOPAX Poseidon. I'd be happy later to give you an opinion, but it would have to be later.
Thank you.
And so
But the first question.
But are you do you work here, or are you like a satellite groupie?
No, I don't work here.
So back to your first question, which was, I think, a geological question. I'm going to put that one over to Tom Farr.
So you're thinking about the lateral transport of groundwater?
The lateral transport of groundwater, in effect, is there any one feature that prevents a groundwater from being distributed properly?
Yeah, it does move horizontally through these basins. It's a fairly long time constant. It can be, it can take centuries to move an appreciable distance. So it depends mainly on the geology. So no, in general, there's no barriers. You can have faults like the Newport Inglewood Fault in LA does present a barrier, but in the Central Valley, there aren't too many barriers. So the water can move freely, but it takes a very long time for it to migrate.
Thank you.
Sure.
You described 4 interlocking processes. What is, in your opinion, I know that you don't have enough data, it's only 10, 12, 15 years, the long-term effect of the climate change, let's say for 100 years or 200 years, on all these 4 processes?
So I'm going to let every one of you have a chance to field that one. Starting with Duane.
I'm sorry, I need a rephrasing of the question. I'm not sure.
So what do you think is the long-term influence of human climate change over the timescale of 100 to 200 years? Is that fair? On those 4 different processes that we kind of touched on in our presentations.
So I think the current research and climate projections that might go out to 100 years in the future indicate that there would be less rainfall falling in kind of the southern latitudes around the world, the sort of substance belt or high pressure regions, and there'd be more rainfall falling to the north of that. So we call it something like the dry gets drier and the wet gets wetter. And that's what the projections look like, the model projections going forward. And there's just a tiny bit of evidence that that may be happening. In fact, Jay showed some things, I guess, earlier today, but not during this talk, that showed evidence of that.
We actually published a paper on that topic that shows with the GRACE data that we're seeing the mid-latitude areas get drier, and the high-latitude areas and the tropics are getting wetter, just in the short time frame of the GRACE data. Is it climate change? Well, give us a few more decades of GRACE satellites and we may know, but it certainly matches what the models predict.
So in terms of the snowpack, as temperatures increase in particular, then the phase of the precipitation, so instead of falling as snow, more of that will fall as rain. And so in the western US, about 80% of the precipitation that falls onto the land comes in the form of snow. About 20% of it comes as rain. And this was a point that tomorrow night's talk is going to have more explicitly. We need to say this, but if you look at the California Department of Water Resources report and others on water supply components in the state, snowpack represents about 30 to 40%, and yet the precipitation is about 80%. What gives? Well, what gives is the groundwater pumping. All right, so that you can have those statements back to back is in fact non-sustainable. All right, you're getting snowfall in 80% to 20% rainfall, and yet in using all of that snowfall, you're using even more water that pushes its proportion down. All right, so that That's why we're going to continue to drop, plain and simple, just the mathematics. Now, in terms of the snowpack and what that does in terms of our water supply, as the phase changes, so as more of the precipitation falls as rain, the human-built reservoirs that we have up in the mountains are going to be tasked with capturing more of that water in the winter, right? Not just in the spring when it's melting. And the staging of that water is an important part of our water infrastructure right now. Right now we have the implicit reservoirs of the mountain snowpack and the human-built reservoirs. And so we have two reservoirs. But as more and more of this falls as rain, it runs downhill right away. Snow doesn't run downhill except in avalanches. Fortunately, not all of our water supply falls or slides as avalanches. But that's going to mean that if we're going to keep the same water supply, some would argue that we need to build more reservoir capacity, right? Others are going to say that's not going to happen, and it would likely be tangled up massively in litigation for a very long time. But what you're looking at is spilling of water over reservoir. If the precipitation stays the same, right? If there's no change, then you're going to see spilling of water over dams and running out into the ocean and essentially shrinking that water supply.
I see a familiar face coming up to the microphone, Ben.
Hi. I have a just quick question. In the pictures you showed of the subsidence, why did the man-made features not drop as well?
Like the pipes and things like that?
Right.
Yeah, the things that didn't appear to drop are things that are rooted way down deep. So like that gas pipeline that was painted orange, that's actually going down, I don't know, hundreds of feet or 1,000 feet. So it's below the area that's compacting. So it's compacting around it, basically.
So even the wells that are kilometers deep, that's not showing that drop as well, then, is what you're saying. So if the well is deeper, is pulling water from deeper than those features, then that would drop those features as well.
That's true, yes.
Okay.
Yes.
Thanks.
Sure.
Hi, I just wanted to say thank you. It was a really interesting lecture. I was wondering, I know you just mentioned that I guess a viable solution would be to build more reservoirs to capture like melting snowpack and stuff like that. But what other viable solutions would there be if the drought continues and we continue to pull groundwater out? And
So as this is meant to be a scientific panel,
yeah.
I'm going to give them a get out. There's some opinions I'm sure at least one of every, the five of us up here could give you, but go ahead. Go ahead.
I'll jump right in. So I think a non-controversial thing is to just use less. So just be, conservation and efficiency are easy and non-controversial and cheap, right? And so if we do as much as we can there, especially in agriculture, we can have a tremendous amount of savings, and I don't think it wouldn't cost billions of dollars.
And that's a big push by all of the water handling entities. So.
Yeah, another thing is what's called managed aquifer recharge. That's essentially another reservoir, treating groundwater as a reservoir. And you can artificially get the water down into the ground. It's not as efficient as other things, but once you get it into the ground, it's less subject to evaporation. So that's really getting a lot of attention right now, and we're looking at that with our radar techniques as well.
So just to say that in Southern California, I think any meeting you go to which involves people involved in water resource management, the theme is sustainability and what they need to do to encourage efficiency in savings, how they make better use of water storage in aquifers, all those kinds of things. That's where they're going to try and get the first savings.
So within cities, there's no doubt that the managed recharge, the sewage recycling, right? We do it in, my home is in Orange County, and we have a world-class sewage recycling facility there. It's called the groundwater replenishment system, and it's great. And if you look around Orange County, it's been able to stay relatively lush compared to the rest of the state because of the management.
Thank you. Let's take
Thank
another
you.
But
question.
there is, real quick, so we didn't say desalination, right? Yeah, desal is a big deal. There are some who want to run an aqueduct from the Columbia River down here. And there are others who want to drag icebergs down here. And I mean, these are all serious
Maybe.
They're serious
recommendations.
Yes.
Exactly.
Yeah.
Okay.
Serious proposal.
Next question, shall we?
I think this is.
Oh, I'm so sorry. Somebody help that young lady.
Oh, thank you. Hi. So, like in a whole presentation, you guys are talking about the climate in USA and California, but we're like, what about like the different region in other places, like maybe in Europe, where they're like, or the climate of a USA might affect the climate in like Europe or Asia? Yeah.
So it's a pretty big question. We chose tonight to focus on California because we thought that as Californians we'd be interested in what's happening to our own local water supply. Is there a quick answer to that, gentlemen?
So I can just give a quick answer on groundwater depletion, and the stuff that I showed for California is happening all over the world. Is happening. Some of the most rapidly depleting aquifers are in India and in the Middle East and in the North China Plain and in Australia and in South America. So it's happening on every continent.
I think it's a very good question. The answers are probably a little bigger than we've even got time to begin to address. Every region is under different kinds of regimes of stress from changes in patterns of climate and weather. But a very good question. Okay.
Thank you.
I think we have one or two questions from online. So, Matheny asks, what would be the most practical way to emulate NASA's GRACE technology in other parts of the world to gauge the effect of El Nino on water resources?
So the GRACE mission is actually a global mission. So it sort of follows on that last question, is that although we only talked about California here tonight, we do have a pretty compelling picture of what's happening. What we saw in California is sort of a microcosm for what's happening all over the world, and it does allow us to see some of the patterns that Duane had. He had a U.S. map that had impacts of El Nino, wetter here, drier there. We can kind of see some of that with GRACE because it is a global mission.
If you guys want the full talk, we can have a Von Karman sleepover. We'll just go all night long.
Just let me go and get a couple of beers and we'll stop.
Well, I can say that the radar techniques are also global, that we're using satellites, and particularly the European one right now is collecting data virtually everywhere in the world. And NASA has a mission that'll fly in about 2021 that will continue those kinds of measurements. So we'll have a continuous time series of these kinds of measurements basically globally. So we'll be looking at many alluvial basins around the world.
Okay, so the next couple of questions from online are not necessarily scientific, so you can express your opinions at this point. Dino asks, are there any programs in place starting to try to preserve as much groundwater and snowpack as we can?
You want to start with groundwater?
No, let's start with snow. It's on top.
All right. So
Over to you, Tom.
That's right. So preserving snowpack. One of the ways that we preserve snowpack is by not changing the phase of precipitation, and so not warming with all of its other implications. The other is that in many parts of the world, there is deposition from desertification, from disturbed lands, of dust on the snowpack, which absorbs sunlight and causes the snowpack to melt away much faster. And in many of those regions, it also causes us to get less total runoff out the rivers. So in the Colorado River Basin, the Bureau of Reclamation and the Bureau of Land Management are considering reducing dust emission from deserts as a way to reclaim water, to supplement the amount of water that's coming in the Colorado River. In the Alps, they're draping they're draping glaciers with mylar sheets to essentially reduce the amount of absorbed sunlight on those glaciers and to cause those to stay up in the mountains so that we have that much longer. So it's one of the things that the World Bank has been working with various scientists that I'm interacting with to pursue is a reduction in particulate load so that we can, particulate being dust and black carbon, to preserve that snowpack, not only within the year, but also over the longer haul and keep those glaciers longer.
So we asked a scientist a question and we got a scientific answer.
You bet.
Actually, I think just to make a comment, I learned from a middle school teacher a few years ago. She was very passionate about preserving beaches and keeping them clean. And one of the things she said is you can make small steps. That's the most important thing you can do. And I think as individuals, you can make one small step in using less water personally. It all adds up.
So I just want to follow up on that, Mike, because it can be pretty daunting, right? When you put all the stuff that you saw together and then you think about the global picture, you might literally want to stick your head in one of, the big sinkholes that Tom was showing us. And so it's important to not get overwhelmed. And right, I mean, do the little bit that you can. Cut back on your watering of your yard. I mean, that's just a small change. And it's a small change that has a big impact.
So here's one more from online. Daniel asks, would California look into atmospheric farming to help meet water needs? And I don't know whether that means cloud seeding, etc.
I think it means vapor harvesting. That's what I thought.
Okay, well, if you think, you can speak.
No, we'll let Duane speak.
Well, I mean, my interpretation was capturing water vapor maybe coming off the ocean surface and making it condense onto something and then capturing it. But I have never heard a tangible or real conversation from the state suggesting that that's something they're seriously considering.
I think most as you guys referred to
But
earlier,
that doesn't mean it's not happening or doesn't exist. It's just,
it does happen, and it's a fairly, so it's actually a fairly primitive technique, right? But if we had a lot of water vapor, then we'd be having rain, right? And so there's not a lot of water vapor. Because it's a dry climate, there's not a lot of water vapor. So it's not really going to yield that much. That being said, I think that if you're like stranded at sea and you have no fresh water, you might want to think about, right, setting up some kind of condensation system.
So with that, stop laughing, Amy. So with that, I'd like to thank our speakers. And if there are any more questions, we're going to be here for a while.
good job, Tom.